order to support our result. So the first task which can be done with the help of econometrics is that each possible determinant that has been considered as the possible determinant, whether it is actually significant determinant or not, that can be studied with the help of econometrics. We can think of all the determinants together. We can take a subset of the determinants. We can take individual items, individual determinant, and try to understand whether this is a significant factor or not. So this is one kind of analysis that can be done with the help of econometrics. Second thing is that whenever we say that these are the possible determinants, we can say that somehow crime rate is related to all these determinants, all or a subset of these determinants. So in that case, if such a relationship can be actually obtained, then there is another thing that can be done with the help of econometrics. It is that if I know the determinants, that is for unemployment, say it is measurable, so we can have data on unemployment, and similarly poverty, so number of poor in the state or in the city, that data will be available, and some items or some determinants are such that data may not be available, but we are not going to that issue right at this point. Our task is to understand what could be done with the help of econometrics. The first thing has been said. The second thing is that if I know the determinants, I will be able to predict what is the crime rate. So if such a relationship can be obtained, the second thing that can be done is that crime rate can be predicted while the determinants are known. So we say that in terms of a mathematical relation, we can say that sometimes we say y depends upon x, and in economics it is often used, the mathematical concept of function is often used, where we say that y is a function of x. That means x is such value of x is used to determine the value of y, or in other words, conceptually we can say that whenever y depends upon x, we can say that y is a function of x. So that kind of thing can be stated here also. We can say that there are certain determinants. For simplicity, we have denoted them by x1, x2, etc. Lot of determinants would be there, and if our crime rate is considered, crime rate is related to such determinants. Now, already it is noted, we may want to examine the validity of such relation. Validity in the sense that we are saying that these are the possible determinants, but whether actually using the data we are finding the same result or not, whether that is a valid relationship, that is whether poverty determines crime rate or not, whether unemployment can determine or unemployment is a determinant of crime rate or not, that can be studied with the help of econometrics. So examining the validity of relations, the determinants, we may try to predict the crime rate. So two things can be done, and econometrics will provide tools by which we can do this. So this is how we build up the concept of econometrics, not necessarily for this particular example. Whenever we see that there is something which depends upon some other determinants, there are some possible determinants, sometimes we want to judge whether such a relationship is actually there using data set, and also sometimes we want to predict the so-called response thing, that is the variable under consideration, which is considered to be the dependent variable on the basis of the known values of the independent variables. So in brief, we can say that two things can be done using econometrics, using data. Of course, relevant variables are to be taken into consideration. We can verify whether there is any kind of significant relationship between that so-called dependent variable and the determinants, and we can guess the crime rate for this example when the determinants are known. So when we verify something according to the idea of statistical inference, we call it testing. We are verifying the relationship, whether such a relationship is valid or not. We try to understand that. And that will be called testing, whereas when we guess, that is when we want to predict the crime rate, determinants being known, that will be called estimation. So this testing and estimation, the tools are available in statistics and that can be used. And I hope the two main objectives of econometrics has been understood, that is verification of the relationship and prediction. So testing and estimation will be the two main objectives of econometrics. Now we deal with a brief theoretical discussion. Just now we have noted that the two things can be done using econometrics, but the question is how it is done. What is the theory behind it? It is not that we are just give certain subjective reasoning and say that this variable will be significant for the dependent variable, this variable will not be significant for. Objective in nature in the sense that there will be mathematical exposition. On the basis of that, we will see it is not based on personal judgment. Formally, it is said that econometrics basically deals with empirical verification of economic theory. Actually, in economic theory, there are various relationships we study. Economics, as students of economics, we understand that most of the cases we start with the law of demand. We say that the demand for a good depends upon such and such factors. Similarly, when we develop, more and more relationships are studied in economics. Formally, we are saying that econometrics will be useful for verification of the relationships which are discussed in economic theory. But actually, the scope of econometrics is not limited to economic theory only. Primarily, we say that it will be dealing with economic theory, but actually, it will be seen that economics, other branches of social sciences, not only that, in many other disciplines, that kind of tools can be useful. Ingredients of econometrics. Just now, it has been mentioned already that economics and mathematics together build up the theory of econometrics. But statistics is also another thing, because from economics we get certain ideas like relationships among variables. For the time being, we are concerned with two variable relationships. For simplicity, we do this. Later, we shall extend this. So, if economics says that y depends upon x, that kind of what is y, what is x, we are not saying that. Y may be some variable, say consumption expenditure, x may be income. So, consumption expenditure, personal level, also dependent upon the income of a consumer. So that kind of relationships are available from economics. There will be certain tools which are provided by mathematics. The tools, already we have used the tool like the concept of function, various other techniques like maximization technique, the minimization techniques, those will be helpful. And also, there will be certain statistical methods. It is also already mentioned, testing and estimation, statistical methods for analyzing empirical data. One example was estimation, the other example was testing, and there are various procedures by which this estimation and testing can be done, and these are the theory of statistics actually provide that. In econometrics, primarily we try to move from economic model to econometric model. Whenever we say y is a function of x, that is, whenever we say y depends upon x, using mathematics, we can say that y is a function of x. Or most of the times we start our discussion with a linear relationship because it will be easy to understand, and in many cases the application of linear relation is a good approximation of other kind of models. That's why we can think of a linear relationship between y and x. And here, y is equal to alpha plus beta x. We know that it is a linear kind of relationship. But the most important thing here is that whenever we say y equal to alpha plus beta x, this is one example of a deterministic relation. Why this is called a deterministic relation? The reason is that provided that I know the values of the parameters alpha beta, whenever x is known, y is known. So y equal to alpha plus beta x actually provides a relationship between y and x in the sense that whenever I know x, I can determine the value of y. Deterministic relation. Of course, provided that I know the values of alpha and beta. Now we are saying that from economic model, we shift to econometric model. We slightly modify the model such that it becomes an econometric model. Note that in the third set, we consider y equal to alpha plus beta x plus something has been added, that is u. Possibly you have observed that. And whenever we add this u, the relation becomes a stochastic relation. Actually, we have added a new variable u, which is such that it is a random variable or it is a stochastic variable. Of course, the question arises, what is meant by a random variable? U is different from x and y for the time being in the sense that u is such that it can take certain values because it is a variable, but which value will be taken by u, we don't know with certainty. So with each value you can take, some probability should be attached because statistics provides at that idea, that is, whenever it is a random variable, then we don't know with certainty the values, but the values will be taken, and for each value we can attach certain probability. So the point is that we are adding u so that the relation is no longer deterministic, it becomes now stochastic. It is stochastic in the sense that for this equation what is happening is that if I know the value of x, I cannot determine y because we don't know u. U is a random variable. Of course, the question arises why this u is added. We shall discuss it later. But for the time being, we can say that whenever we say y is a function of x, for example, if we say personal consumption expenditure depends upon income, then we can say it is an economic model because there is a theory behind it or there is some empirical observation behind this, and logically we can build up such an equation. So we say that it is an economic model. But whenever we add this stochastic term or the random variable u, then the equation becomes stochastic relation. No longer it is a deterministic relation, and the model will be called an econometric model. Now what we notice is that the first step in any econometric study would be inclusion of this u. Inclusion of the u will make the equation stochastic. Inclusion of u will make the model economic model. We come to that point. What?
इनको भेज दीजिए, लिंक भेज दीजिए ग्रुप का, वही एक एक नोजिया
the structure of the equation. This will be called the regression equation. Y on x, first of all, we notice that and there are two variables x and y. It is called two variable because x and y, of course u is another variable,
बोलिए कि उस पे जुड़िए,
but u is unobservable. We don't have any data on u. That is the difference. Now X and Y
और वो
are
जिन्होंने
originally in the
ये
model,
जिन्होंने रजिस्टर
and
किया है ये लोग
so
जुड़े
we
नहीं
call
आपस
it a
में,
two
रजिस्टर
variable
करके छोड़
model.
दिए हैं आपस में
Second
डिबेट
thing
कर
is
रहे हैं,
that
विभिन्न
in econometrics we can deal with more than one variable.
हाँ उनको
That
परसेंटेज
type of model is beyond our scope right at this moment. So there can be simultaneous model also, but we are dealing with one equation. That's why we call it a single equation. Another point, we have considered it is a linear model. Already we have discussed that a linear equation has some simplicity, and for that reason, at least we can say that we start with a linear model, and the model has been constructed in such a manner that the variables are such that the model is linear in variables as well as parameters. There will be various other kinds of models, we shall discuss it later, but for the moment it is to be noted that the model is linear in both in variable and in parameters. Different terminology are used. First of all, this x, since y has been expressed in terms of x must be the independent variable and y must be the dependent variable. And when we say that y is dependent variable, x is independent variable, and we express y in terms of x, it will be called regression equation of y on x. Various other terms are used. Alpha, beta. Alpha will be called the intercept term, already written. Beta is regression coefficient. The two parameters are there. And dependent variable is also called explained variable. It is also called regression. And independent variable is called explanatory variable and regression. The thing is that when we consider y as a function of x, we treat y as the dependent variable, x as the independent variable. So if the task is to explain the variation in y, then we say y must be the explained variable. In our example, we tried to explain crime rate. Why crime rate changes in different cities? What is the reason behind such variation? We tried to analyze that. So y must be the dependent variable, and for that reason we can say that y is also called the explained variable. In a two variable model, we can think of a relationship between crime rate and unemployment level. So in that case, y, the crime rate, will be regressed on unemployment rate, and so unemployment is the factor that will try to explain the variation in crime rate. That's why unemployment can be considered as explanatory variable, the variable which will explain the variation in y. So in that model, our task will be to analyze the variation in crime rate by means of variation in unemployment. That's why other terminologies which are used are like this: independent dependent variables, explanatory explained variables, and also sometimes we say regressor. X is regressor here and y is called regressand. We have added this u. We are yet to explain why this u has been added, but the name of u in econometrics is that it is called the disturbance term, and it is also called the error term. Now the question is why this U has been included in the model. We have noted that in order to make an economic model to an econometric model, the relation must be stochastic, not deterministic. But definitely the question arises why this U should be included. The first reason is that if you look back that first slide, if you just think of that, we considered possible determinants of crime rate. We have tried to add as many as possible. But the thing is that sometimes it is not possible to include all the explanatory variables. What could be the reason? So the first reason is that we want to capture the effects of omitted variable in a model. We started with a model where crime rate was the dependent variable and lot of explanatory variables have been considered. And at the end, I put some question mark. The reason is that sometimes we are not aware of all the factors that could affect the dependent variable. In this case, we have prepared a list of factors or determinants that can affect crime rate. But we cannot claim that the list is exhaustive. Maybe we are not aware of existence of many other factors that could affect crime rate. It is possible. Another reason may be that we were aware of, but those were not measurable. And also, those are measurable, but data were not available. That is also possible. So there are several reasons why, in a model, some explanatory variables are included and some are not included. Those are excluded. Sometimes we don't know existence of such factors. We are not aware of that such factors could affect the dependent variable. Sometimes it happens that we were aware of, but we could not collect the data. Data were not available. Sometimes data were available, but due to non-availability of data, it was not possible. And also there will be another constraint that will come later. Number of observations and number of parameters in the model, there must be some connection. Number of observations always should be more than the number of parameters in the model. So for all these reasons, it is possible that there are certain variables which are included in the model and certain variables are not included in the model. Those are omitted variables. So when we omit certain variable, we cannot say that the dependent variable is not at all affected by those factors. We admit that there are other factors which are omitted in the model, but they have impact on the dependent variable. But for some reason, we have omitted in the existing model. So you will be included in the model. The first reason is that we want to capture the impact of those omitted variables on the dependent variable. So for example, if I just consider the regression equation of crime rate on poverty and unemployment, some index of poverty and unemployment rate, then the impact of all of the factors are supposed to be captured by these two. So this is the first reason why the error term is added in any econometric model. Second thing is that sometimes it is found that the dependent variable is not reported correctly. We have collected data on the variable, but sometimes the actual value of the dependent variable is different from the data which have been collected. One example which is often suggested is that income. When we ask for the document, it is a different thing. But suppose we ask the people, what is your income? What is the profit from your company? So in that case, it is possible that they are not giving the actual value of the dependent variable, and so there will be a discrepancy between the actual value and the reported value, and that is termed as the measurement error. And if there is any measurement error in the dependent variable, that can be captured by this disturbance term. So this is the second reason why U is included. Third thing is that we want to incorporate the aspect of randomness. Already we have said that the econometric model will include U such that the model becomes econometric, that means the relation becomes stochastic relation. Why? What is the importance of randomness? See, in economics, we deal with practically human behavior, and there is some randomness in human behavior that is inherent in the nature of human behavior. Suppose we are with the amount of purchase of a good. We understand that the demand for the good depends upon a lot of factors. In introductory economics, it is taught what are the factors on which demand for a good will be dependent. Suppose we are concerned with individual demand. Even if all factors remain same, it is not that the same person will be purchasing the same quantity every day. Today I go to the market, I see the price and other factors, I decide how much to purchase. Tomorrow I go to the market. For some reason, even if all the factors remain same, still I won't purchase the same quantity. And this is the randomness, the kind of randomness that can be explained in economics. There is inherent randomness in human behavior, and we try to capture that. Suppose we are concerned with a production function. Production of a good is related to the input level. There is relationship between output and inputs. So it is not that if the input levels remain same, always the production will remain same. Such kind of deterministic relationship is not actually correct for economic analysis. Rather, the econometric model will be the correct one. Some kind of uncertainty will be there. We want to capture the role of uncertainty in the model, and for that reason we include U also. So basically, U is included in the model in order to incorporate all these aspects. We build up a model, we want to analyze the impact of one variable on other variable, we want to analyze the impact of several variables on a single variable. We understand that the model is such that we cannot claim that all explanatory variables have been included in the model. That's why we keep this U inclusive in the model. Second reason, we understand that when we collect data, there may be some kind of error in the collection of data, that is the actual value of the dependent variable is different from which has been reported. For that reason also you can capture that measurement error. And the third reason is that we want to make the relationship stochastic, that is we want to incorporate the aspect of randomness in human behavior. So these are the three reasons why this U is included in a model. And the point is that whenever we study econometrics, the starting point is the inclusion of this disturbance term. And you can look at the next slide and you can understand what is the importance of inclusion of this U. As I have said that inclusion of U is the first thing which is done in any econometric analysis. Already we have discussed this, why this U is included. Second point we shall discuss will be that what are the assumptions on it. In economics, we know that we often make our life simple, and we try to analyze something, we try to understand something as if life is very simple. We make certain violate those assumptions and we come closer to reality. So it is not that the economic study is meaningless because it is dependent upon a lot of assumptions. Initially we make such assumptions. The assumptions seem to be very restrictive. Those are different from the reality. But ultimately, after studying the things in a simple model, in economics, it is the orientation of the subject of economics that we try to come closer and closer to reality by relaxing those assumptions. And when we relax those simplifying assumptions, we come closer and closer to reality. That will be done. First, we consider very simple model. So certain assumptions will be made, and the model will be called the classical model. After that, we try to understand. Already we have noted what are the objectives of studying econometrics. Verification and prediction will be done, which is in statistical terminology called testing and estimation. How these are done? Under the assumption that these assumptions are true. What will be the problem? Next question arises, if these assumptions are violated, then what will happen? And we will see that we will face problem if such assumptions are violated. Then definitely, if there is a problem, what will be the consequences on the and testing procedure? Is in the model how to test test whether such problems are there or not, how to detect that kind of problem. That will be another thing which will be done. After that, if after testing we find that yes, the testing procedure is such that the result shows that such a problem is there, how testing will be done, because our ultimate goal is to test the validity of the relationship and to test the or predict the dependent variable. So when certain simplifying assumptions are there, how the estimation and testing are done, and if such assumptions are violated, then also how estimation and testing will be done, that will be the subject matter of econometric introductory econometrics rather. So many other things can be done, but primarily our concern will be revolving around the inclusion of U. So all these matters are such that these are related to inclusion of U. So one by one we try to answer these questions. First of all, using the example from consumption and production, we have said that we need a stochastic model. But since we shall deal with data, how can we explain why we need a stochastic model? Suppose we take xy plane, two variables are there, x and y, and we draw a scatter diagram. We know what is a scatter diagram. We just collect in pairs of observations on x and y. X and y must be some related variables, and when we plot each pair of observation by means of a dot and collect all such dots for all the endpoints, then we get a diagram, and the diagram is called a scatter diagram. Suppose the scatter diagram looks like this. So it is very unlikely that we get a scatter diagram where all the dots lie on a single straight line. It is very unlikely. Usually we get a scatter diagram like this. Now you can observe the statement which has been made at the bottom. Take any value of x. Notice that there can be more than one value of y. Suppose I take a value x here. Draw a vertical line. On the vertical line, exactly we cannot say that if x value is this, y value must be given by this. Because for that we need a straight line on which all the dots should lie. Otherwise, what would happen? Whenever we get a value of x, actually there are more than one value of y. And in terms of statistics, we say that there is a probability distribution of the values of y. For the moment, we are not going detail on that thing. We are just noting that all dots will not lie on a single straight line. Rather, the scatter diagram looks. This is one possible scatter diagram. There are many other forms that can be noted. Already it has been said that what assumptions we primarily impose on the model. This model is called the classical linear regression model, in short CLRM. We have added UI and C in observations are there. Basic four assumptions are these. First of all, since we are saying that U is a random variable, there must be some probability distribution of U. Whenever it is probability distribution, the connected concepts are expectation of U and expectation of functions of U. And the concept of expected value, concept of variance, covariance between U values, etc. are there. In classical model, the simplifying assumptions are these: expected value of Ui is equal to 0 for all I. For any observation, the expected value should be 0. Second thing is that when we try to consider variance, that must be a constant. Variance of Ui is a constant, again for all observations. So if for the first observation I take U1, expected value of u1 is 0. Similarly, expected value of u2 is 0. And even for the nth observation, expected value of un is also equal to 0. If I take first observation u1, u1 will have a probability distribution. And if I compute the variance, what is variance in statistics? The definition is available. Variance shows the variation of u values, and we take deviation. It is a measure of variation in u values. That variation of u1 is sigma square. And see, for all I, that means if I take u2, then also the variation must be same. That is, over observations, always the variation in the error term is a constant. And this is again a simplifying assumption. In reality, for all kinds of data, it is not that always we find that this assumption will hold. So there will be certain kind of data for which it is not expected that the second assumption is true. And then we have to consider violation of the second assumption and see how we can detect it, how estimation can be done, etc. Similarly, from one observation to another observation, if I take the covariances, then the covariance must be 0. See, here we have taken covariance between ui and uj, and covariance between ui and uj will be 0 for I not equal to j. And x is non-stochastic. This is once again, it is a simplifying assumption. U has been considered to be stochastic variable and x is considered to be non-stochastic. Since y has two parts, one part is x, the other part is u. And already we have said that u is the stochastic variable. So in that case, y must be a stochastic variable because one component is non-stochastic, the other component is stochastic. Another thing, in advanced model, we can assume that the x is also stochastic. That is also possible. But initially, when we start our discussion, we take x to be non-stochastic. That will simplify our life. We can make it complicated, assuming that x is also stochastic. So now primarily y has one component which is called the intercept term, the other component beta into xi plus ui. Here, when we consider this regression equation of y on x, what is the importance of the parameters alpha and beta? That must be understood. See, beta is the coefficient of the explanatory term. It is a parameter. Of course, we don't know the values of beta, we don't know the value of alpha. Our task will be to utilize data on x and y. Already it has been noted that we don't have any data on u. And when we consider beta, this coefficient, it is very important for us. What does it tell? That must be understood properly. Because ultimately, what will happen is that after knowing something, a bit from the theoretical idea, the theoretical results, it is very easy to estimate alpha beta. It is very easy to testing thing. But what is to be tested, that must be understood. And for that reason, what is the importance of beta, that must be understood properly. See, since we have a linear equation here, when we consider x, the coefficient is fixed, that is understood. But the thing is that this beta is very important in the sense that if we change this xi by 1 unit, then the amount by which y will change must be beta. That is the point. But there is a but. The thing is that u must be constant. If we had one deterministic relation, if u were not there, then if I know the value of x, I could determine the value of y, and that equation would be called the deterministic relation. And in that case, we could say that when x increases by 1 unit, y will increase by beta units. But now we have u. So unless we say that u remains fixed, this beta will not give us the impact of x on y. So we must add these things, other things remaining constant, beta will show the impact of x on y. That is the importance of this coefficient. And since in a linear model this beta is fixed, we can say that the impact of x on y will be fixed. It is independent of the value of x. For a non-linear model, it will be variable. But since we are dealing with a linear model, we understand that whenever x changes, x changes by 1 unit, y must change by beta unit. But other things remaining constant, that must be added. So it is called the ceteris paribus impact of x on y. So this terminology is often used in economics. It means that other things remaining constant, because we see that this u captures the impact of other variables and there are other reasons. And mathematically we can say that unless we keep the value of u, we cannot say that when x increases by some unit, y must increase by beta into that much of amount. So we have to consider the significance of this term beta in the sense that this beta will show the impact of x on y provided that other factors are unchanged. Whenever we have more than one here we have considered only one explanatory variable, because it is a two variable model. But we could have more than one variable, and in that case also the coefficient will show the impact of that particular variable on the other on the dependent variable, other things remaining same. And in that case, the other things will include not only the impact of the omitted variables, but the impact of other included variables. So later we shall deal with that. If time permits, we shall deal with that. So it is our linear equation. These are the assumptions which are made primarily. And now, meeting the two objectives, how estimation is done and how verification is done. We plot the data on x and y in a scatter diagram. It looks like this. See, if this scatter diagram is found, the actual relationship between x and y is embodied in this diagram. For some points we find that when x increases, y increases. For other points when x increases, y decreases. A few points are there. Usually it is found that the dots are such that the dots cluster around the positively sloped straight line. So we think that higher values of y are associated with higher values of x, and lower values of y are associated with lower values of x. That kind of observation is made. The second point noted is that the dots cluster around a positively sloped straight line. Actually, it is not the second point, it is the same point from another approach we can say it. Here we are saying that the dots cluster around a positively sloped straight line. We can superimpose a positively sloped straight line. But which straight line? Which straight line will fit the data best? That is, our task will be to identify the best fitted line. We are given certain data. Using the data, if I actually try to observe the relationship, it may look like this. But we want to represent the relationship between y and x by means of a single line. Why we want that? Because the relationship is such that the regression equation is such that it includes u. It includes u. So even if we know alpha beta, it is not possible to predict the value of y when I know x. I hope you get the point. When we have a deterministic relation, y equal to alpha plus beta x, provided that I know the values of alpha beta, whenever I know x, I can get the value of y. But here, there is u, and u is unobservable. We don't have any data on u. So even when alpha beta are known, supposed to be known. If x value is given, I cannot get the corresponding value of y, because disturbs. It is the disturbance term. I cannot get the value of y whenever x is known. So what can be done? So we can say that yes, it is true that I cannot find the values of alpha and beta, but econometrics will provide the tools. I can utilize data. I can estimate the values of alpha and beta, and we shall call it alpha hat, beta hat, and as the estimated value. That is, we don't know. It is true that it is never possible to find the values of alpha and beta. There is a population regression function, and alpha beta are connected with the population regression function. It is never possible to find the values of alpha and beta, but econometrics will provide the tools which can be utilized to estimate the values of alpha and beta. Graphically, what we can say that if we consider the data set, the diagram, scatter diagram looks like this, but I want a single straight line to represent this data set, and I want to identify the best fitted line, that means which will describe the relationship between x and y most efficiently. Whenever we say this thing, one point is there. What shall we do with that straight line? What shall we do with alpha hat and beta hat? Why we need that? Already we face the problem that since u is there, we cannot utilize the stochastic relation to predict the value of y. So what we can do? If we can somehow estimate the relationship, we get y hat, the estimated value, in terms of x. Then it looks like a deterministic relation. But it is not the deterministic relation between x and y, rather it is the relationship between x and y hat. Y hat will give us the estimated value. It is not the actual value, it is the estimated value. So, if such an equation is available, y hat equal to alpha hat plus beta hat x, then whenever x value is known, we get the value of y hat. And since y hat need not be same as y, we will say it is the estimated value. It is the predicted value. We cannot claim that y and y hat will be same, rather it is the predicted or estimated value. Graphically, we can say that our first objective will be the best fitted line will pass through the x bar y bar point. So this is our objective. We want a straight line to represent the data, and passing through x bar y bar, we can draw actually numerous straight lines. An infinite number of straight lines can be drawn through x bar y bar points. In the class fin, the teacher used to say that through x bar y bar, if it is asked to draw the straight line, each one of the student will draw. It is possible that draw a different line because their intercept and strokes are different. Choose the best fitted line. Which line should be chosen? Definitely, that is the question. And it should not be subjective. I cannot say that I prefer blue color, that's why the blue line should be the best line. I cannot say that. So there must be some objective criterion behind it. And for why part is important. See. Whichever line is taken as the best fitted line, there must be error. If you superimpose the scatter diagram on this, you understand that there are certain points which will lie above the best fitted line. Till now, we have known what is the best fitted line. We are trying to develop a criterion for choosing the best fitted line. What we observe is that if I claim that the blue line must be the best fitted line, I must justify why it is the best fitted line. If someone says the red line is the best fitted line, that person must justify why that is the best fitted line. So for that we need a criterion. What we observe is that when the scatter diagram looks like that, it is true that there is a straight line around which the dots cluster, but all dots do not lie on the same straight line. we cannot find a single straight line on which all the dots will lie. Some points will be above it, some points will be below it, and in this diagram we have identified a few points. The pink points are such that they are above the base fitted line and the green points are below it, and some points of course lie on the base fitted line. So what we can say is that if I utilize this line for prediction or estimation, what will happen? If x is here at this point, let me use the pen. Suppose x is here. X is here. Then if I use this straight line for prediction, I would estimate y by this value. So this is the length. But the actual value is here. The data shows the observed value is here. So the error is definitely there. This is the amount of error, this length, this vertical distance. Similarly, if it lies below, then still there is error. So incidentally for these blue points there is no error. So whenever we try to identify the base fitted line, we understand that through the scatter, practically we can draw numerous straight lines passing through the point x bar y bar, but we need one straight line as the base fitted line, and we can think of several things because several criteria practically, because we understand that whatever line I choose, there must be some error. Obviously, the first thing which we can suggest is that I choose that line for which I choose. Yes, this is our equation for base fitted line, and suppose it is found that it is the error for the ith observation is defined in this manner. Vertical distance has been translated in this form using algebra. Criterion 1. Whenever we admit that there must be error, we may try to minimize it. So we may try to first minimize the total amount of error, summation ei. Another criterion is this. Why we suggest an alternative criterion? The reason behind this is that whenever we compute summation ei, we understand that some errors will be positive, some errors will be negative, and if we add them, that will not give us the correct amount of error involved in the process, because positive negative things will be reduced. The actual amount of error is not reflected by this. So clearly it may be suggested that either criterion 2 or criterion 3 can be used. That is, we can try to minimize the sum of absolute values of ei, or alternatively sum of squares of ei. And the criterion 3 will be better because it is easy to consider certain mathematical calculations using square terms. So criterion 3 is preferred, and criterion 1 is totally useless. This technique, see, is such that we try to use a criterion where sum of squares of errors will be minimized. That's why we use the name least squares criterion. And there will be other kind of least squares estimation in econometrics. That's why this one is called ordinary least squares method. So the problem will be to choose alpha hat and beta hat such that summation ei square is minimum. Alpha hat is the Wales estimator and beta hat is Wales estimator of beta. The expressions will be this. I hope I am not disconnected. Let me check. Okay. We are familiar with calculation of covariance variance. I have told that the calculations will be avoided. We just concentrate on the final result. So if xy values are available, we can compute the sum of product, and n is the number of observation, x bar is the mean of x, y bar is the mean of y, x bar square, and it is sum of squares. So this way we can compute alpha hat and beta hat. These violet things, these few things are the essential calculus. The entire page is not needed. This part will be needed. This part will be needed. Estimated regression equation already mentioned. Beta hat, these are several alternative expressions, and this standard error. This is very much needed. Very much needed. Standard error calculation. How it is computed, that is available in any of the textbooks of econometrics. Better we learn what is the important. We try to use as a proxy for beta. Beta we can never compute, already we have said. So in case of beta, we shall use beta hat. Similarly, alpha can never be computed in the population regression function. Alpha is there, we cannot compute it. So we use this formula for getting an idea about alpha. Alpha hat is the Welles estimator. Now, when we say that beta hat is used for beta, definitely we cannot say that beta hat is equal to beta. We cannot claim that. But if beta hat is close to beta, that will be better. And so in that case, we look into at least two characteristics. One characteristic is that whether the expected value of beta hat is equal to beta. So we understand that beta hat could be more than beta, beta hat could be less than beta. But if on an average, that is expected value of beta hat is equal to beta, then we accept beta hat as a good estimator. But that is not enough. Beta hat, the expected value is equal to beta. But it is found that beta hat is much deviated from beta. That is also possible. So in that case, the variance in beta hat is also another important factor. And whenever we compute it, ultimately, we take the square root of variance, which is the standard deviation. And since error variance will be there, the u is the error term, and the variance is not known. Since u is not observable, we cannot compute sigma square, the variance of u, and that will be utilized. And this part will give us the error variances unbiased estimator. So all these things are available in textbooks, but our point is that why computation of standard error will be needed. One thing is clear from this slide, that is, first of all, we try to understand whether beta hat will be a good estimator of beta. For that, we compute expected value of beta hat, and in order to understand that, the standard error is to be computed. There are definitely other reasons why this standard error will be needed. It is needed because when we conduct the testing part, then it will be very much needed. For estimation purpose, up to this it is okay. These are other theoretical results which are obtained in any two variable model, and this result is very significant result. Each one is significant, but this is very useful. This fourth one, this left hand side is called the total sum of square. It shows, it is actually a measure of total variation in y, and this part shows the variation in y which is explained by the regression model, and it is the unexplained part. So it is very important to note that when the least square technique is used, we can compute the left hand side, we can compute the right hand side, the two components of the right hand side. And the significance of the result is that total sum of square can be decomposed into the explained sum of square and the residual sum of square. That means whenever we try to explain explain variation in y by means of the explanatory variable x, we understand that the total variation in y will have two parts. One part will be explained by x, the other part will not be explained by the regression model, that remains unexplained. And since the total variation can be decomposed into the explained part and unexplained part, we get some measure r square. See, the numerator is such that it is this first component, and the denominator is such that it is this is the total, this left hand side. That means this r square, this ratio shows the proportion of variation in the variable which is explained by the regression model. It is very significant result. Suppose for a model we find that the value is close to 1, say 90%. Then we can say that our model is very good. We have included the explanatory variable. It is so significant that it can explain 90% of the variation in the dependent variable. That's why this result is very significant. So this is one thing, and this is one theorem which is suggesting why the least square estimator is considered to be the best estimator. Already we have explained that its expected value is to be considered, taken into consideration. This is one reason why it is considered to be a good measure, good estimator. Beta hat can be shown to be a linear function of the dependent variable. It is linear and it is based because we can have more than one unbiased estimator, but from among all the linear unbiased estimators, the least square estimator will have the minimum variance. The deviation will be least from the expected value. That's why it is considered to be the best linear unbiased estimator. So this is the way by which we justify why the OLS technique will be suggested when the assumptions are satisfied, provided that the CLRM assumptions are satisfied. This is another thing which will be useful. Already we have noted this thing, the R square can be written in this form. But one point is there, although R square shows the proportion of variation in the dependent variable which is explained by the regression model, we cannot use this as a measure of goodness of fit, because there is one observation. On the basis of that, we see this thing. Whenever till now we have considered two variable model, that is there is a single regression. Single regression means there is a single explanatory variable. But when we add more explanatory variables in the right hand side, it is found that this numerator, that is ESS, never falls. It can increase, it can remain same. So in that case, there is a temptation by the econometrician is to include more and more variables in the right hand side, so that even if they are not at all related to the dependent variable, still there is a chance that it will increase. So it is like negative mark. It is like not having any negative marking. I don't know the answer of all questions. I attempt all the questions in the hope that even if I give a wrong answer, still my marks will increase. Chance that if it is correct, it will increase. So in order to correct this difficulty, some alternative measure is suggested. It is like this. It is called the adjusted R square. It is called the adjusted R square. Adjusted R square we have corrected in this manner. Here K is the number of parameters estimated, and we understand that whenever we increase the number of explanatory variables in a model, then connected with that, more parameters will be there. Coefficients, number of coefficients will be more, and so number of parameters estimated will be more. And we can notice that mathematically R square never decreases due to increase in number of variables, explanatory variables. But if K increases, this adjusted R square may decrease also. So it is used as a measure of goodness of fit because it captures or it imposes a penalty for including more explanatory variable in the model. This is the observation. So one objective has been fulfilled, that is how to estimate the model. Alpha hat, beta hat can be estimated using the formula. We have seen that how to estimate it, and when alpha hat, beta hat have been estimated for any value of x, we can utilize the estimated equation to predict the value of y. Now the second objective. Second objective, what we want to do? We want to study whether the relationship is valid or not. The theory is very interesting. See, original model is yi equal to alpha plus beta xi plus ui. We want to test this null hypothesis. As I said, this beta is very important because beta shows the impact of x on y, other things remaining constant. We see that if beta is a 0, mathematically, what does it mean? X has no impact on y. Similarly, if beta is non-zero, x has impact on y. So we use this beta equal to 0 as the null hypothesis. So in any hypothesis testing, what is the null hypothesis? That is very important. And second thing is that what is the alternative hypothesis? Because the alternative hypothesis will be utilized in order to understand what will be the critical value which will be collected from statistical table. So the method is such that here we need one additional assumption because we need the probability distribution. Already we have said that U has a probability distribution, but which distribution it follows, we have not mentioned anything about that. Actually, we have not required it. At this point, we cannot proceed further unless we exactly know which distribution UI will follow. And till now, we have not yet said, but at this moment we are assuming that UI follows normal distribution. Under this assumption, there is a result that if we compute this value, this will be a t variable. There is another related variable, t distribution is there, and it will be a t distribution, and the parameter, the degrees of freedom will be n minus 2. This 2 is coming from the number of parameters to be estimated. In this model, since alpha and beta are the two parameters, number of observations n, from that 2 must be subtracted. So if we take a k variable model, 1 is dependent and k minus 1 independent variable. K minus 1 independent variable, so k minus 1 coefficient and the intercept term, so k parameters will be there. So in that case, these degrees of freedom will be n minus k there. Anyway, so for this model, this is the result, and from that, under H naught in statistics, we know that it means the complete statement is under the assumption that the null hypothesis is true. So if the null hypothesis is true, beta is equal to 0. So it boils down to this expression, and this is called the test statistic. Test statistic. So test statistic, already we have seen how to compute the standard error of beta hat. That's why I said that the standard error is very important in testing. So this can be calculated using the particular formula. Beta hat can be computed, so we get the value of t, and that will give us the observed value of t. What is the rule? The rule is this: H naught is rejected at 5% level of significance if the observed value of t is greater than critical t. First of all, the importance of alternative hypothesis is there. Since it is not equal to type, that means a two-tailed test is to be used. Accordingly, we decide what should be the critical value. Second thing is that not only it depends upon the alternative test, alternative hypothesis, it depends upon the level of significance. What is level of significance? We understand that even if the null hypothesis is true, there is chance that it will be rejected. So because it is one of the shortcoming of the procedure, that we understand that while using the sampling theory, it is possible that the null hypothesis was actually true, but using the sample, it is possible that the test statistic falls in the critical region. That's why we have rejected it. So, and this is termed as the type 1 error. And so here this 5% level of significance means it is the probability of that type 1 error. So H naught is rejected at 5% level of significance since it is a two-tailed test, half of 5%, which is 0.025 that has been taken, and already noted that it is the degrees of freedom is n minus 2. That's why it is taken. Observe T, the absolute value is taken because it is a two-tailed test, and not only that, the t distribution is a symmetric distribution. That's why we have taken this, and these are based on the statistical inference theory, and if needed, that part is to be revised so that it is clearly understood why this is the observed t which is compared with the critical t, and this value can be obtained from statistical table, and we just check whether this value is more than this or not. And if I change this 5% to 1%, conventionally 1% or 5% are taken into consideration. Accordingly, this value will change. And if it is a two-tailed test, instead of two-tailed test, if we have one-tailed test, accordingly we take 0.05 or 0.01, or also minus also can be taken into consideration depending upon again the alternative hypothesis. Accept the null hypothesis otherwise. See, this is the testing procedure. So when practically we apply it, what we shall do? Using one example, we can clarify it more, but this is the basic idea. This much theory at least is needed. This is assumption of linearity. Let's skip these things. Since we shall be dealing with data, first of all, we need to know what are the three kinds of data usually we use: cross-section data, time series data, and panel data. We started with two charts. In the first chart, you remember that we consider the variation in crime rate over time. That means for a particular country, one variable and how it changes over time. Here, suppose we are concerned with the first row, Afghanistan. For Afghanistan, the life expectancy at birth in years for different years. So this row can be called a time series because it shows the observations on a variable over time, and consecutive time periods have been considered. Similarly, for each country, there is a time series. If we take a particular column, suppose I take 2006. For 2006, a number of countries are there and data are there. And so we can say it is a cross-section data. And if we take the entire data set, it will be called panel data. Basically, these are the three different types of data: cross-section data, where different entities for a single time period, time series data, and panel data. These are the three kinds of data we shall use. We use one cross-section data and try to apply this. Because after all, econometrics is such that only theory is definitely not interesting much. And second thing is that are not much clear, I think so. This is our objective. Think that this is one possible determinant, one of the possible determinants. We take a two variable model for simplicity. First of all, we need to justify why we think that this is a factor which will explain life expectancy of the countries. We take cross-section data, number of countries, a particular year. This is our model, and see, it has been included. That means it is now an econometric model that must be included in any econometric model. Now we want to test this beta equal to 0. If beta equal to 0, it means per capita GNI has no impact on life expectancy. That means there is no valid relationship between them. And if beta is not equal to 0, there is a relationship. The entire data set has not been shown. The calculations are shown. Finally, alpha hat, beta hat are calculated, and this is the result. So this is the regression equation of y on x. Other calculations are needed because standard errors are to be calculated. All calculations are not shown. Finally, how to report the data, how to present the regression output, that is to be noted very carefully. So how to present the regression result? When we present the regression result, first of all, we write down the estimated equation. See, the value of alpha hat, it is the value of y hat. Strictly speaking, one hat must be there after this life expectancy. Above it, one hat must be, because it is the it is the estimated value. And we write t, within bracket we write this, and at the bottom it has been mentioned that the figures indicate the t values, corresponding t values. R square is to be reported, and adjusted R square is also reported. So a few things are to be reported. Alpha hat, beta hat, that means the regression equation in estimated form, t values, R square, and adjusted R square. Instead of t values, sometimes the t statistics, instead of that, sometimes p values are reported, but since we have not yet dealt with that, I have not mentioned anything about that. It is one form of representation. In place of t, we could present the p values also. The ultimate task is to interpret the result. So the regression output has been obtained. We have calculated it manually using Excel, but actually many softwares are there. Econometric softwares are there. Even Excel itself is useful for regression analysis. Simple regression analysis can be done using Excel. All these things can be easily computed using the software. The task will be only to enter the data and give the instruction. The regression output will come within a few seconds. But the ultimate goal is to interpret the result. The task of the econometrics today is to interpret the result. For interpretation, what we shall say? Just have a look once again. This is the result, and now the interpretation. We need to interpret a few things. The sign of beta hat, the magnitude of beta hat, whether the coefficient, the estimated coefficient is statistically significant or not, these three things. Then the value of R square is to be interpreted, and the value of adjusted R square. These few things are to be done. See, one by one it has been done. Beta hat was found to be this. We interpret it in this manner. We say that it is expected to have a positive impact. It is very important that since we are using data and our study will be based on a sample, we cannot claim that always it is true that GNI per capita will have positive impact on life expectancy. We very humbly say that our data shows that GNI per capita have positive impact. So it is expected to have positive impact on life expectancy, or data support the belief that GNI per capita has positive impact on life expectancy. This is the indication. But when we consider this, I first consider the sign, then I consider the magnitude. Apparently, the magnitude is very small, 0.001 0.0002. So we say that according to our interpretation, if GNI per capita increases by 1 unit, life expectancy will increase by this much unit. This much unit. So 0.0002, it is very small. But what is the unit of measurement? I tried to measure it specifically for this example. GNI per capita, the data were collected from the World Development Indicators. That's why it was measured in dollars. And the result indicates that $1 increase in GNI per capita may lead to increase in life expectancy by this much of year. In year, it is that value, but if we ultimately convert it into hours, 2 hours, we can say that it is not bad. If $1 increase may lead to increase in life expectancy by 2 hours, it's not bad. But the point is that whether the coefficient is actually significant or not, beta hat significant or not. For that, the verification part will be necessary. This is done on the basis of estimation. Now the verification part will be important. Observed value of t.
Akash, please mute yourself. Akash, mute yourself. Akash, please mute yourself. Akash. Akash, please mute yourself.
विकेट कीपर है, बैट्समैन है, इंडिया है, कप्तान भी है, इंडियन है, कप्तान, इसलिए दिक्कत है, सबसे अच्छा ये टी20 का अच्छा प्लेयर है। 20 करोड़।
Okay. Observe T for beta hat will be found to be this. And this is the critical T available from statistical table. See, number of observations were 32 and 2 parameters were to be estimated. So the degrees of freedom was 32 minus 2, it is 30. There is a comma here, and it is the critical T. From table we find this value 2.042, and so we come to the conclusion that observed T is greater than critical T. Therefore, the null hypothesis must be rejected. What were the null hypothesis? Beta equal to 0, and beta equal to 0, it means that GNI per capita does not rejected. That means the alternative hypothesis is to be accepted. So alternative hypothesis means beta not equal to 0, and it indicates that the relationship is valid. That is, our data or our analysis indicate that there is impact of GNI per capita on life expectancy because it is statistically significant. Statistically significant means the value falls in the critical region. If it is in the critical region, we reject the null hypothesis. Actually, for this problem, we are happy that the null hypothesis is rejected. So, our belief that life expectancy could be affected by GNI per capita is supported by this analysis. We cannot claim that always it is true that whenever per capita GNI increases, life expectancy will necessarily increase. We cannot claim that. Because after all, our have been taken, which period has been taken, definitely it is dependent upon that. So we conclude that for this data set, this may be a valid relation. We cannot say that it is a valid relation. We say this may be a valid relation. Next is interpretation of value of R square. It is found to be 0.49. We say that 49% of variation in life expectancy is explained by our model. So we cannot say that it is a very good model. because the value is not close to 1. And also we cannot say that it is a poor fit because the value is close to 0. Some observation is there. And the measure of goodness of fit is found to be 0.47. So this is how interpretation is done. So whenever we interpret, whenever we conduct any similar type of empirical study, we have to first present the regression output. When we present the regression output, first we mention the estimated equation and corresponding t statistic or the p-value, r square, adjusted r square. Next task will be to interpret the result. While interpreting this, we don't just say that beta hat is statistically significant. No, that is not enough. Beta has impact on that particular y. So that type of analysis will be done. Similarly, r square can be interpreted in this manner, and adjusted r square, the measure of goodness of fit is less than 50%. Not good, this much we can say, but not too bad. Extensions. So these are basically the introductory time, and in one day we cannot learn everything. Definitely econometrics is a vast subject, and every day it is developing. Various extensions are there. At this moment we just try to know what are the various other extensions that can be done in order to conduct a meaningful econometric study. First of all, including more than one regressors. This is obviously one extension that can be made. So far we have considered only one explanatory variable x. Only one explanatory variable x means it is a two-variable model, and it is called a simple linear regression model. If we include more than one regression, more than one explanatory variable, that model is called MLRM, multiple linear regression model. More than one regression or more than one explanatory variable. When we consider that the similar least squares technique will be available, but obviously when we compute alpha hat beta hat, the formula will be such that it is a bit complicated compared to the simple linear regression model. And the name itself, simple linear regression model, it is simple. And then when we move to multiple linear, definitely it will not be so simple. It must be a bit complicated. The expressions will be a bit complicated, but the same technique can be used, provided that the classical linear regression models assumptions are fulfilled. One confusion arises whether a model is CLRM and MLRM at the same time or not. Is it possible that this SLRM is also called CLRM? Question is not regarding that. When we say it is a CLRM, it means the assumptions with which we have started, those assumptions are fulfilled. If we find that those assumptions are not fulfilled, then that model is not considered to be classical model. Otherwise it is classical. So far the assumptions are fulfilled. Regarding simple model and multiple SLRM and MLRM, the difference is that how many regressors are there. If there is one regression, then it is SLRM. Now, whether the assumptions are fulfilled or not, that does not mean that it is not SLRM. Suppose we have a model where only one regressor is there. That is two-variable model. But all the assumptions of CLRM are not fulfilled. Then it is SLRM, but not CLRM. Similarly, if we have MLRM, then one regressor, that is 3-variable model, 4-variable model, 100 variable model, one dependent and 99 independent variable, MLRM. Now, can you say that this model is not a CLRM? Yes, it can be a CLRM. If all those assumptions are fulfilled, it is MLRM as well as CLRM. But If the assumptions are not fulfilled, then it is MLRM but not CLRM. So it is not that when it is CLRM, it must be SLRM. No. When it is MLRM, it cannot be CLRM. No. CLRM, whether assumptions are fulfilled or not. SLRM and MLRM, different thing. Number of regression is the matter on the basis of which distinguish between SLRM and MLRM. Another point is to be added here. While considering any simple linear regression model, we started with a few assumptions. One more assumption is to be added in a CLRM when it is with more than one regression. See, among the regressors, there may be correlation. It is possible. Suppose we take the example like say environmental degradation. One indicator has been taken, environmental degradation, and in the right hand side, suppose as explanatory variable we take income, and also we take income inequality. Now in that case, the two regressors in the right hand side are such that they may be related. So if there is any association among the explanatory variables, then there will be a problem. This problem is called multicollinearity. In case of SLRMC, there is no possibility that there will be multicollinearity because there is a single regression and the correlation or association among the regressors, the question does not arise at all. So for any multiple linear regression model, we must think of one additional assumption, that is, the regressors should not be perfectly correlated. One additional assumption is needed. And regarding MLRM, how it is better than SLRM, if we try to understand that, already we noted that if we add more variables in the right hand side, it will be better because one reason is that we have said that the impact of X and Y is captured by beta provided by other factors are fixed. But whether other factors are fixed or not, whether we are controlling the other variables or not, that cannot be actually done, practically done, unless we conduct some multiple linear regression model. In a multiple linear regression model, if we have more than one variable in the right hand side as explanatory variable, controlling for other variables, we can study the impact of one variable on the other. So a meaningful econometric study can be done in multiple linear regression model. But we cannot say that the simple linear regression model is totally useless. It is not. There are conditions under which SLRM can give us reasonably good result. It is also possible. So there are many more complications. We cannot deal with each one because that will take a 1 hour class separately. Another thing that can be done as extension is that qualitative regression. Possibly the third slide, it shows the determinants of the variable. I listed a number of variables. Among them, some variables were such that they are qualitative in nature. That is, those are not variable. So certain characters are such that whether suppose we consider the gender of a person. Gender we cannot measure it. Either we can have male or we can have female, we can have third gender. So different categories we can consider. So here the categorical variable will be taken into consideration. So regression is such that we have to take into consideration qualitative regression. Those are not measurable. And here something which is called a dummy variable that will be used in order to capture the impact of such regressors. That is one more possible extension of the basic idea. Next thing is violation of assumptions of CLRM. This is very interesting thing because so far we have considered the assumptions of CLRM are valid. So we have started with the thing that provided that the assumptions of CLRM are valid, how the estimation and verification or testing can be done. We have completed that part, but we are yet to answer that part, that is, if those assumptions are violated, then what will happen? Briefly, we touch up that thing. That is one possible extension. That's why we shall deal with that. Using various alternative functional forms. I skipped one slide, possibly you remember that. It seems that the classical linear regression model is very restrictive, that it can deal with only linear models. The model should be linear in variables, the model should be linear in parameters. No, not at all. It seems that it is very restrictive, but actually not. Provided that the model is linear in parameters, several alternative models can be studied. We can take a model where y is regressed on x square. If y is regressed on x square, in place of x in the equation we use x square. So definitely it is a nonlinear type of relation, and for nonlinear type of relation, it is possible to apply the same technique, the ordinary least square method, that can be done, provided that it is linear in parameters. So, although it seems that the classical linear regression model is very restrictive, but actually it is possible to modify the various models in the form of a linear model, and then we can apply the same technique. So this is another possible extension. Model selection. It is definitely very important, because which variables are to be included as explanatory variables, which variables are to be omitted, how many variables are to be taken into consideration in the model, that must be understood. And regarding that, if I include some irrelevant variable, then what will happen? If I do not include some relevant variable, then what will be the impact? So will it be better to omit certain variables which are irrelevant or relevant? So on the basis of what we decide which variables are to be included and which variables are not to be included in the model. So model selection, what should be the functional form? Should we take linear form or we take some non-linear form? As I said that y can be regressed on x. So far we have considered that. But I have mentioned that y could be regressed on x square also. Log y could be regressed on x, log y could be regressed on log x. So which model will be better? Which functional form? And what will happen if there is some misspecification? Misspecification, that is, some relevant variable has been excluded, the functional form is wrong, some irrelevant variable has been included, what will be the impact? So that study will be possible extension. So we look at the violation to some extent, violation of assumptions. Violating the first assumption, expected value of ui equal to 0, will not it is not at all a problem, but this is one problem. It is called problem of heteroscedasticity. If we violate the second assumption, variance of ui is a constant for each I, if we violate that, it is called the problem of heteroscedasticity. Mainly it is found in cross-section data. And the scatter diagram looks like this. In place of heteroscedasticity, it is often suggested that it depends upon the value of x, how the variation of u changes. These are the possible sources, cross-section data. Outlier, there is extreme values presence, inclusion of explanatory variables, distributions are skewed. These are the possible sources. Consequences, we look at this. If I still run OLS, then what would happen? Still it will be unbiased, but it will no longer be the best estimator, because it will lose the property of having minimum variance. And in that case, the conventional t-test, we cannot rely upon that, and forecasting will be unbiased but not reliable. And detection, there are various possible ways by which detect it. I skip these things because no more time is there. Another thing, in a classical linear regression model, if we relax the third assumption, zero covariance between u values, if we relax that assumption, then we face a problem. It is called autocorrelation. Among the U values, there is correlation. So let's skip this. We just look at the sources and the consequences. These are the sources, time series data mainly, and prolonged influence of shocks like COVID, etc. In that case, it is possible that the U values, the omitted variables, will be correlated. Spatial correlation, autocorrelation. This is also possible, not necessarily for time series data. Geographical aspect also taken into consideration. It is possible that there is misspecification is another possible source. These are the consequences. And it is similar to the consequences of having heteroscedasticity in the model. Multicollinearity is another problem if we have more than one regression in the model, and if we relax that assumption that no exact collinearity or among the regressors, then we face the problem that it is not possible to disentangle the impact of one variable, because if the variables and the explanatory variables are correlated, then such problem will arise. There are various tests that can be conducted in textbooks. You will find it. One very famous test is Darwin-Watson test. If time permits, I could show it, but there is no more time, and the remaining days you will study many other things. Some are multivariate analysis and principal component analysis that will be taught. And in the context of multivariate analysis, principal component analysis will be very important, because already we have noted that how many explanatory variables have to be included in the model. That is a big concern. And it is sometimes needed to understand the overall impact of some variables. It is not needed individually. We want to study the impact of one variable on the dependent variable. In that case, the principal component analysis will be very much helpful in multivariate analysis. Time series regression, it is already noted that time series data are such that over time the variables observations will be there. And in that case, what we find is that two things can be noted. First of all, when we consider the variable under consideration may be a trending variable. Trending variable means over time the value increases or over time the value decreases. In that case, it is very likely that the mean value and the variance will change over time. And in that case, if we make any prediction on the basis of the regression analysis, that will not be reliable unless the variable under consideration is stationary. So the question of stationarity will be very important there, and whether there is any long-term relationship between two variables. That is, if both the variables are trending under time series, then the problem of the aspect of co-integration that will be studied. So this is just the mention of those things. Panel data analysis, we have noted what is meant by panel data. And panel data, we understand that it is a combination of both cross-section and time series data. It will be very helpful for regression analysis, because both country to country variation and variation over time both can be analyzed in the same model. Binary dependent variable model, sometimes it is found that the dependent variable can take only two values, binary in nature, whether the person is happy or unhappy. So in that case, the probability that the person will be happy, suppose it is considered to be 1 and it is 0 otherwise. So it can take just two values, 0 and 1. For that kind of cases, various type of models like topic model, logic model, topic models, etc. will be under this binary dependent variable models. Spatial regression, this is also another idea where it is found that the dependent variable is such that there is they are autoregressive. That is, the geographical aspect is there. The observations on Y are related. So for that kind of cases, how to conduct the regression analysis? So these things will be taught, and also stepwise regression, that will be also covered in this workshop, because here already we have noted that in model selection, which variable is to be included and which is to be excluded from the model. Step by step regression, we use some iterative method, that is, we include and exclude the variables in order to ultimately get the final model. So this is the things which will be covered in the rest of the days. And I am talking for the last 2 hours. I could not get a chance to interact with you. So now, if time permits, you can ask me the question. Whatever I wanted to say, that has been covered.
Thank you so much, ma'am. Thank you. As you have asked, if the time permits, yes, the participants, if they really want to, if they have some queries, they can come up with their questions. Otherwise, I think that, ma'am, you have incorporated and you have summarized in such a lucid manner the entire lecture that you have given, a prologue that really it gives a meaning. The introductory lecture has really covered every aspect which we are going to study in the coming days. And as far as you have given a brief picture of what is the difference between basically the CLRM, SLRM and MLRM, that was very interesting. Because at times actually tend to confuse, and the assumptions of CLRM, when it actually get fulfilled, then only we can say that yes, whether we can categorize it to SLRM or MLRM. Otherwise, CLRM is quite important. That was very interesting part that you have actually make us understand. And besides that, the PPT was so well organized, so well in such a enhanced manner that you have given your deliberation. I think that each of the participants have really been enriched by whatever you have actually tried to explain them. Still, I would request any of the participants, if you would like to ask any question to ma'am, you can please come up with your query. We have just 2 minutes time. Yes.
Thank you, ma'am, for your feedback. It's very encouraging for me. Yes.
Ma'am, actually, econometrics is such a is actually a subject which many of us find really difficult, because the way
it is not. It is not. I don't really.
That is general perception, ma'am. A general perception that there is a difficulty in understanding. But I feel that the whoever must have learned from you will just not say this anymore, that it is a difficult subject, because you have explained this in such a flow manner that yes, it has actually seeped it into us, and we are really looking forward to learn so many advanced models that you have actually you have just noted us. And very interesting part of that certain concepts like autocorrelation, heteroscedasticity, multicollinearity, then panel data analysis, then these certain things really need to be comprehended, because many of the queries came to me by the research scholars that they are working on primary data and they just don't know how to go about this to actually put in the econometric tools over here. Simple statistical, fine, but when it comes to the econometric tools, they really get worried. But I think that, ma'am, we have, you have given your consent for this lecture, and a introductory lecture actually boosts up for the remaining lectures. So I will again extend my heartfelt gratitude to you. I think that no one has come up with any questions.
I have one question. Can I
yes,
ask?
Dr. Arjun Singh, please come up.
Ma'am, I have actually I don't have question. I have on one confusion, that is, what is the relation between research methodology and econometrics? What I understand is actually the relation of data, that is primary data, and econometrics is only secondary database. Is I right now or something?
Yes. When it is time series data, we try to understand over time what is happening. But if it is cross section in a particular year, from country to country, from one entity to another entity,
sorry, ma'am, my question
such variation is there.
My question is how research methodology and econometrics are correlated.
Research methodology in econometrics, so far what we have learned today is that it is related to cross-section analysis. And in time series, the difference I have pointed out, that for time series analysis, the difference is that we have to take into consideration stationarity of each variable under study before conducting the regression. Second thing is that we have to think of possibility of long-term relationship among them and also the short-term relationship. And when it is panel data, we try to consider the between. Between means from one group to another group, what is the variation, and over time, what is the variation. So within a particular group, what is the variation, and from one group to another group. Suppose you take 30 years and 10 countries, suppose. In that case, for a particular country, what is the variation, and within the country, what is the variation, you study that. And again, from one country to another country, what is the variation? Both can be captured in a panel data. Obviously, the technique will be different, it will be much more complicated. So we have considered only the simple things in the sense that we have taken the cross-section data, the two variable model, and obviously if we consider the such extensions which have been pointed out, obviously the models will more and more complicated. And ultimately, if we move for panel data, and there are many other advanced models, I have pointed out only those things which will be covered in here, and not in definitely in detail. Only the primary idea about the things.
Thank you, ma'am. Actually, Dr. Arjun saying what I can comprehend from your question that, whenever we actually go with any kind of a research and we have to write in the research methodology, then you want to ask the relationship how econometrics is actually used. It is very much used because it gives the tools and techniques of how to go with the data. Because when the quantitative, actually you see, what basically is econometrics, it is actually defined as a quantitative analysis. And then in research methodology, we need to do the quantitative analysis of actual economic phenomena, which is based on the concurrent development of theory and observation. So we need to actually put in what methods we have to apply to get the inference out of it. So in that category of research methodology, we actually use these econometric tools and techniques, and so they are correlated.
Thank you, ma'am.
Okay, thank you. Anyone else? Well, ma'am, I extend my heartfelt gratitude once again to you for making us, anything. We just kept on listening to you. You were so very composed and at a subtle voice. The PPT was very informative. I'm getting all the chat messages that they want your PPT, the effort that you have put in. But I think that the way you have presented, and because we are recording this, I must tell you, ma'am, that for this online workshop, we have got the participation from all over nation, from north to south, from east to west. Yes, ma'am. So like they are hearing you and they are getting enriched by you, and we can see so many responses. Thank you, ma'am.
Opportunity. I have got the opportunity to share my.
Manisha ma'am wants to say something. Yes, please.
Yes, ma'am. Good evening. Smita ma'am, good evening. I have a question.
Yes.
थोड़ा टफ की वजह से थोड़ा लेट हुआ. Ma'am, I am a research scholar and currently I face a situation. बहुत फर्स्ट और मेरी फर्स्ट स्लाइड से ही डाउट है कि how to decide whether a variable would be a dependent variable and a other will be an independent variable first, and then what if as we have taken crime rate in the particular point, crime rate as a dependent variable and a lot of regressors was there. Ma'am, what if as some of the variables, as by observation I observed that some of the independent variables found to have or are having a relationship that are switch in nature, that is crime rate will be treated as a independent variable and the other variables that were treated as an independent variable will be considered as dependent variable. In that situation, how will we decide what will be the dependent and independent variable?
See,
Yes,
when I have shown the simple example where life expectancy was regressed on that per capita GNI, there the first line I wrote is justification. So justification means either using theory or intuitive idea, you have to explain why you think that this is the dependent variable and this is the independent variable. So if I practically want to conduct such an analysis, like I want to explain the crime rate variation over the different metropolitan cities in our country, suppose I want to conduct such studies, then first of all, for each variable I have to justify. So I said that we can argue on that, so whether this variable should be taken into consideration or not. So primarily, when we construct any econometric model, we have to justify it. That's why in that slide I have shown that the justification, that must be one particular point. Just randomly we should not say crime rate is regressed on such and such variables. We have to justify our model. While we think that, now after conducting the study, what is your observation? You maybe you expected that poverty would have
Yes, ma'am.
positive crime rate. You expected that.
Yes, ma'am.
Finally, you come to the conclusion that the expected the estimated coefficient is found to be negative. So in that case, your conclusion would be that it is of unexpected sign. Our expectation was that it would be like that, but it is found to be negative. Suppose.
Yes, ma'am.
So in that case, you say unanticipated sign. So
Okay.
first of all, you need to justify for each variable. Randomly, here I have shown it as an example. I am not actually conducting the study.
Yes.
So Manisha, when you conduct the study, you will have to justify.
And even some of the variables, yes, and you as you have pointed out, some of the variables as the regressions, they are related. So we have to take one from them.
Okay,
So
ma'am. Apart from theoretical point of view, apart from theoretical understanding, is there any tool, as you mentioned, you can check the relationship between regressors? That is, you are indicating towards multicollinearity.
yes, it will deal with the problem of multicollinearity. There it will be dealt with. Model
And
selection.
one more question, please. Ma'am, I conducted a study and I framed a multiple linear regression equation having three models and different equations were there. And in my study, GDP was the dependent variable, whereas independent variable or regressors consisting of expenditure, revenue, expenditure and revenue, first model. On the other hand, second model comprises of GDP same, real GDP same as the dependent variable, and on the other hand independent variable was net fiscal deficit. And the third model may I found the effect of what kind of what mode of financing is found to be suitable in case of Indian economy to just fill the gap between expenditure and revenue. That is it internal borrowing or external borrowing? So, ma'am, my reviewer, as I prepared a paper, and reviewer asked a question about the interrelationship, about the two-way causality. He said GDP also influence the independent variables. Then how
Yes,
can you
yes.
say?
There can be simultaneity also.
Yes, ma'am.
In this restrictive discussion, we considered only single equation model. There could be simultaneous model also.
Yes, ma'am.
So if it is found that your variable, say we have I have used one example, environmental degradation and economic inequality, income inequality.
Income
So
inequality.
there could be two-way relationship, isn't it?
Yes, ma'am.
So in that case, simultaneous model will be a better model.
Okay, simultaneous equation model, right?
Simultaneous.
Okay, बाकी
Yes.
मैम आप जैसे
So
जैसे
instead of single equation model, you could, yes.
Okay, ma'am. Thank you.
Thank you so much, ma'am. Thank you so much for giving your time and your consent. Thank you so much. And thank you all participants. We shall be meeting tomorrow again online at 3 p.m. and we shall be giving the feedback form in the participant group as well. Thank you so much for joining us.
One question
Yes,
from
ma'am.
my side.
Yes,
If
ma'am.
I like to join any of the
Yes,
session,
ma'am. Yes, ma'am. You are there for all the 7 days. You are invited, ma'am. You are most welcome.
and thank you very
Thank you,
much.
ma'am. Thank you.
That life expectancy could be affected by GNI per capita is supported by this analysis. We cannot claim that always it is true that whenever per capita GNI increases, life expectancy will necessarily increase. We cannot claim that. Because after all, our studies have been taken, which period has been taken, definitely it is dependent upon that. So we conclude that for this data set, this may be a valid relation. We cannot say that it is a valid relation, we say this may be a valid relation. Next is interpretation of value of R square. It is found to be 0.49. We say that 49% of variation in life expectancy is explained by our model. So we cannot say that it is a very good model because the value is not close to 1. And also we cannot say that it is a poor fit because the value is close to 0. Some observation is there. And the measure of goodness of fit is found to be 0.47. So this is how interpretation is done. So whenever we interpret, whenever we conduct any similar type of empirical study, we have to first present the regression output. When we present the regression output, first we mention the estimated equation and corresponding t statistic or the p-value, r square, adjusted r square. Next task will be to interpret the result. While interpreting this, we don't just say that beta hat is statistically significant. No, that is not enough. Beta has impact on that particular y. So that type of analysis will be done. Similarly, r square can be interpreted in this manner and adjusted r square. The measure of goodness of fit is less than 50%. Not good, this much we can say, but not too bad. Extensions. So these are basically the introductory time, and in one day we cannot learn everything. Definitely econometrics is a vast subject and every day it is developing. Various extensions are there. At this moment, we just try to know what are the various other extensions that can be done in order to conduct a meaningful econometric study. First of all, including more than one regressors. This is obviously one extension that can be made. So far we have considered only one explanatory variable x. Only one explanatory variable x means it is a two-variable model and it is called a simple linear regression model. If we include more than one regression, more than one explanatory variable, variable, that model is called MLRM, multiple linear regression model. More than one regression or more than one explanatory variable. When we consider that the similar least squares technique will be available, but obviously when we compute alpha and beta hat, the formula will be such that it is a bit complicated compared to the simple linear regression model. And the name itself simple linear regression model, it is simple. And then when we move to multiple linear, definitely it will not be so simple. It must be a bit complicated. The expressions will be a bit complicated, but the same technique can be used, provided that the classical linear regression models assumptions are fulfilled. One confusion arises whether a model is CLRM and MLRM at the same time or not. Is it possible that this SLRM is also called CLRM? Question is not regarding that. When we say it is a CLRM, it means the assumptions with which we have started, those assumptions are fulfilled. If we find that those assumptions are not fulfilled, then that model is not considered to be classical model. Otherwise, it is classical. So far, the assumptions are fulfilled. Regarding simple model and multiple SLRM and MLRM, the difference is that how many regressors are there. If there is one regression, then it is SLRM. Now, whether the assumptions are fulfilled or not, that does not mean that it is not SLRM. Suppose we have a model where only one regressor is there. That is two variable model. But all the assumptions of CLRM are not fulfilled. Then it is SLRM, but not CLRM. Similarly, if we have MLRM, then one regressor, that is 3 variable model, 4 variable model, 100 variable model, 1 dependent and 99 independent variable, MLRM. Now, can you say that this model is not a CLRM? Yes, it can be a CLRM. If all those assumptions are fulfilled, it is MLRM as well as CLRM. But if the assumptions are not fulfilled, then it is MLRM but not CLRM. So, it is not that when it is CLRM, it must be SLRM. No. When it is MLRM, it cannot be CLRM. No. CLRM, whether assumptions are fulfilled or not. SLRM and MLRM, different thing. Number of regression is the matter on the basis of which distinguish between SLRM and MLRM. Another point is to be added here. While considering any simple linear regression model, we started with a few assumptions. One more assumption is to be added in a CLRM when it is with more than one regression. See, among the regressors, there may be correlation. It is possible. Suppose we take the example like say environmental degradation. One indicator has been taken, environmental degradation, and in the right hand side, suppose as explanatory variable we take income, and also we take income inequality. Now in that case, the two regressors in the right hand side are such that they may be related. So if there is any association among the explanatory variables, then there will be a problem. This problem is called multicollinearity. In case of SLRMC, there is no possibility that there will be multicollinearity because there is a single regression and the correlation or association among the regressors, the question does not arise at all. So, for any multiple linear regression model, we must think of one additional assumption, that is, the regressors should not be perfectly correlated. One additional assumption is needed. And regarding MLRM, how it is better than SLRM? If we try to understand that, already we noted that if we add more variables in the right hand side, it will be better because one reason is that we have said that the impact of X and Y is captured by beta provided by other factors are fixed. But whether other factors are fixed or not, whether we are controlling the other variables or not, that cannot be actually done, practically done, unless we conduct some multiple linear regression model. In a multiple linear regression model, if we have more than one variable in the right hand side as explanatory variable, controlling for other variables, we can study the impact of one variable on the other. So, a meaningful econometric study can be done in multiple linear regression model. But we cannot say that the simple linear regression model is totally useless. It is not. There are conditions under which SLRM can give us reasonably good result. It is also possible. So there are many more complications. We cannot deal with each one because that will take a 1 hour class separately. Another thing that can be done as extension is that qualitative regression. The third slide, it shows the determinants of the variable. I listed a number of variables. Among them, some variables were such that they are qualitative in nature. That is, those are not variable. So certain characters are such that whether suppose we consider the gender of a person. Gender we cannot measure it. Either we can have male or we can have female, we can have third gender. So different categories we can consider. So here the categorical variable will be taken into consideration. So regression is such that we have to take into consideration qualitative regression. Those are not measurable. And here something which is called a dummy variable that will be used in order to capture the impact of such regressions. That is one more possible extension of the basic idea. Next thing is violation of assumptions of CLRM. This is very interesting thing because so far we have considered the assumptions of CLRM are valid. So we have started with the thing that provided that the assumptions of CLRM are valid, how the estimation and verification or testing can be done. We have completed that part, but we are yet to answer that part, that is, if those assumptions are violated, then what will happen? Briefly, we touch up that thing. That is one possible extension. That's why we shall deal with that. Using various alternative functional forms. I skipped one slide, possibly you remember that. It seems that the classical linear regression model is very restrictive, that it can deal with only linear models. The model should be linear in variables, the model should be linear in parameters. No, not at all. It seems that it is very restrictive, but actually not. Provided that the model is linear in parameters, several alternative models can be studied. We can take a model where y is regressed on x square. If y is regressed on x square, in place of x in the equation we use x square. So definitely it is a nonlinear type of relation, and for nonlinear type of relation, it is possible to apply the same technique, the ordinary least square method, that can be done, provided that it is linear in parameters. So although it seems that the classical linear regression model is very restrictive, but actually it is possible to modify the various models in the form of a linear model, and then we can apply the same technique. So this is another possible extension. Model selection, it is definitely very important, because which variables are to be included as explanatory variables, which variables are to be omitted, how many variables are to be taken into consideration in the model, that must be understood. And regarding that, if I include some irrelevant variable, then what will happen? If I do not include some relevant variable, then what will be the impact? So will it be better to omit certain variables which are irrelevant or relevant? So on the basis of what we decide which variables are to be included and which variables are not to be included in the model. So model selection, what should be the functional form? Should we take linear form or we take some non-linear form? As I said that y can be regressed on x. So far we have considered that. But I have mentioned that y could be regressed on x square also. Log y could be regressed on x, log y could be regressed on log x. So which model will be better? Which functional form? And what will happen if there is some misspecification, that is some relevant variable has been excluded, the functional form is wrong, some irrelevant variable has been included, what will be the impact? So that study will be possible extension. So we look at the violation to some extent, violation of assumptions. Violating the first assumption, expected value of ui equal to 0, will not it is not at all a problem, but this is one problem. It is called problem of heteroscedasticity. If we violate the second assumption, variance of ui is a constant for each I, if we violate that, it is called the problem of heteroscedasticity. Mainly it is found in cross-section data. And the scatter diagram looks like this. In place of heteroscedasticity, it is often suggested that it depends upon the value of x, how the variation of u changes. These are the possible sources, cross-section data. Outlier, there is extreme values presence, inclusion of explanatory variables, distributions are skewed. These are the possible sources. Consequences, we look at this. If I still run OLS, then what would happen? Still it will be unbiased, but it will no longer be the best estimator because it will lose the property of having minimum variance. And in that case, the conventional t-test, we cannot rely upon that, and forecasting will be unbiased but not reliable. And detection, there are various possible ways by which detect it. I skip these things because no more time is there. Another thing, in a classical linear regression model, if we relax the third assumption, zero covariance between u values, if we relax that assumption, then we face a problem. It is called autocorrelation. Among the u values, there is correlation. So let's skip this. We just look at the sources and the consequences. These are the sources, time series data mainly, and prolonged influence of shocks like COVID, etc. In that case, it is possible that the u values, the omitted variables, will be correlated. Spatial correlation, autocorrelation. This is also possible, not necessarily for time series data. Geographical aspect also taken into consideration. It is possible that there is misspecification is another possible source. These are the consequences. And it is similar to the consequences of having heteroscedasticity in the model. Multicollinearity is another problem if we have more than one regression in the model, and if we relax that assumption that no exact collinearity or among the regressors, then we face the problem that it is not possible to disentangle the impact of one variable, because if the variables, the explanatory variables are correlated, then such problem will arise. There are various tests that can be conducted in textbooks. You will find it. One very famous test is Darwin-Watson test. If time permits, I could show it, but there is no more time. And the remaining days, you will study many other things. Some are multivariate analysis and principal component analysis that will be taught. And in the context of multivariate analysis, principal component analysis will be very important, because already we have noted that how many explanatory variables are to be included in the model, that is a big concern. And it is sometimes needed to understand the overall impact of some variables. It is not needed individually. We want to study the impact of one variable on the dependent variable. In that case, the principal component analysis will be very much helpful, in multivariate analysis. Time series regression, it is already noted that time series data are such that over time the variables observations will be there, and in that case what we find is that two things can be noted. First of all, when we consider the variable under consideration may be a trending variable. Trending variable means over time the value increases or over time the value decreases. In that case, it is very likely that the mean value and the variance will change over time. And in that case, if we make any prediction on the basis of the regression analysis, that will not be reliable unless the variable under consideration is stationary. So the question of stationarity will be very important there, and whether there is any long-term relationship between two variables. That is, if both the variables are trending under time series, then the problem of the aspect of co-integration that will be studied. So this is just the mention of those things. Panel data analysis, we have noted what is meant by panel data. And panel data, we understand that it is a combination of both cross-section and time series data. It will be very helpful for regression analysis because both country to country variation and variation over time both can be analyzed in the same model. Binary dependent variable model, sometimes it is found that the dependent variable can take only two values, binary in nature, whether the person is happy or unhappy. So in that case, the probability that the person will be happy, suppose it is considered to be 1 and it is 0 otherwise. So it can take just two values, 0 and 1. For that kind of cases, various type of models like topic model, logic model, topic models, etc. will be under this binary dependent variable models. Spatial regression, this is also another idea where it is found that the dependent variable is such that there is they are autoregressive. That is, the geographical aspect is there. The observations on Y are related. So for that kind of cases, how to conduct the regression analysis. So these things will be taught, and also stepwise regression, that will be also covered in this workshop, because here already we have noted that in model selection, which variable is to be included and which is to be excluded from the model. Step by step regression, we use some iterative method, that we include and exclude the variables in order to ultimately get the final model. So this is the things which will be covered in the rest of the days. And I am talking for the last 2 hours. I could not get a chance to interact with you. So now, if time permits, you can ask me the question. Whatever I wanted to say, that has been covered.
Thank you so much, ma'am. Thank you. As you have asked,